Hi, this is Logan Spawn, and today I'm going to be presenting on case study number 3. So first I want to start off by going over the problem. The control system we're going to be looking at today is an unmanned, free-swimming submersible vehicle as shown in that picture. The goal of this project is to reduce error while the vehicle rises and submerges. To do that, we're going to find steady-state error, reduce it by adding a lag compensator, and then eliminate it at ESS by introducing a PI compensator. So in part A, we need to find our original steady-state error in order to reduce it. So I first found zeta using the percent overshoot given based off my birthday, which is February 11th, and the equation relating the two as shown. I then moved on to that block diagram on the right. I simplified it to unity feedback by moving k over and then combining the blocks in cascade form. Using this, I plotted the root locus to find my gain k, which ended up being 6.47. Using this k value, I then was able to calculate the original steady-state error. So on the left there is a root locus plot showing my gain, and then on the right there's a formula that I used to find my steady-state error of 0.134. So moving on to part B. In this part we want to reduce steady-state error by a factor of 10. So to do this, we start by finding a new KPN, or a static error constant, using our desired steady-state error. This allows us to find ZC, and then after choosing an appropriate pole that is close to a zero so as to not to shoot that is close to zero so you don't shift it too far right, we get our compensator that we implement into the original transfer function. I then plotted the root locus of the new GC to get a compensated gain. So there's that. I expected the compensated system to have a shorter rise time and settling time than the uncompensated. However, as you can see here, the compensated system has a higher peak time and rise time and settling time, just worse performance characteristics. And that compensated one is the red one. So as you can see, it takes more time to get to the top, has a higher peak, and then takes more time to even settle. But it does settle closer to 1, which is what we want. That's the reducing of error that we're trying to achieve here. And here I just put the peak time, rise time, and settling time, just comparing them just to show again that the uncompensated system has better performance characteristics than the lag compensated system. Okay, now for part C. This time we want to reduce the steady state error all the way down to 0. So I did this by using a PI proportional integral compensator that is able to reduce the steady state error to 0 due to the form of its transfer function, k times s plus zc over s. This decreases the type from type, or increases, the type from type 0 to type 1. Taking the limit of the control transfer function as it approaches 0, we get kp equals infinity and therefore steady state error equal to 0. So I plotted the new system, and using my same zeta, I found a new k. And then I plotted the new system response versus the uncompensated system as seen here, with again the compensated system being the red. So similarly, the PI controlled has worse performance characteristics than the uncompensated system, but the error this time is all the way down to 0, which is ideal. So now, which one is better? Part B or Part C? So to determine this, I just took a look at those performance characteristics side by side, peak time, rise time, and settling time. As you can see here, the PI controlled has better performance characteristics and it reduces the error all the way down to 0, making it my personal choice for the best compensator for this system. Thank you for listening.